So the final thing that we'd like to have is some measure of efficiency. Whenever I twist this, I'm putting a certain amount of energy in, and when I'm lifting something and doing actual work with it, or compressing a spring, or which is anything this is squeezing is kind of like compressing a spring, I'm getting energy out of it. And some of the energy that I put in, though, is taken up by the friction at this interface, at the thread interface. It's also taken up by the collar. And so we'd like to know what is the ratio of the work that I get out to the work that I put in. And we can get that by, here I'm going to erase a little bit. Okay, so the work that I put in, so the input versus the output. The work that I put in comes in the form of I put in a torque, and then that gets multiplied by some sort of displacement, theta. And then the output is going to be the force, at the top of the clamp, times whatever amount that it displaces. I'll say d. Actually, that's a bad choice. I'm going to say delta because d is reserved for major diameter. And so the efficiency then, is going to be the ratio of those two. Is going to be F delta, the amount that I get out, over T theta. We know what F is. That's the same F as all throughout these equations. That's the same. Yeah, this is this F. What's the torque? The torque is the sum of any collar friction torque plus maybe the torque to raise something. It's the sum of those two things. Theta turns out isn't going to matter because we need to figure out what delta is. Delta, it turns out, is expressed in terms of theta. We know that there is a definite relation. We know the relationship. It's not affected by friction. It's not affected by anything. It's only affected by the pitch or the lead of the screw, what the relationship is between delta and theta. It's just a matter of kinematics. And so we know that we go, when we turn the screw, the lead is the relationship between the amount of turns, 2 pi, a full turn, and how far it goes. So we know that in one full turn, we get the lead, L, for every 2 pi. That's how far we go. If we multiply that times theta, that ratio times theta, that's going to be equal to delta. What's the better way of putting that? Maybe, delta over L is equal to theta over 2 pi. Does that make sense? Theta over 2 pi. However much we turn over 2 pi, one full revolution, is delta over, maybe delta over, here we go. Delta, maybe an easier way to say it is delta over theta is the same as L over 2 pi. The amount we go translationally over the amount we turn it, that's equal to the relationship between the amount we go in one full turn and 2 pi, one full turn. Okay? So what we're after is this form of the relationship, L over 2 pi times theta. Okay? So that means that we can write our torque input as T. Let's say it's the T that TR. Let's leave it as T, the whole torque, the full amount of torque. It's the R plus TC. I'll say T total, just so you remember that it's the total torque that you have to put in. And then F delta is just, we're going to change that to F times L theta over 2 pi. Okay. Well, no, I'll just write this as F delta. I'll make the substitution down here. This is equal to F times L times theta over T 2 pi times theta. The thetas cancel each other out. And so this just becomes FL over 2 pi times T total. TOT. TOT. That's our efficiency.